C and C++ provides two pointer operators, and they are address of operator, which we went through in a different video. And the other one is indirection, or sometimes we refer to it as the reference operator, start. Both of these are unary operators serving different functions on pointers. Recall that a pointer is a variable that contains the address of another variable, or you can say that a variable that contains the address of another variable is said to point to the other variable. A variable can have any data type, including an object, structure, or again, pointer itself. The address of operator is simply one that returns the memory address of its operand. In the next couple of slides, let's look at both of them. Firstly, we will review addresses of operator using some examples. Say we have a double variable called double val, initializing it to 0.0, and we try to print out the address of double val. This is valid because double val takes up 8 bytes of memory space at runtime, which means double val has a memory address. Therefore, when you ampersand this double val, you're getting the actual address of that double val sitting in memory. And this memory is on the stack. We can also assign a memory address of another variable to it. What we have here is uninitialized variable. It doesn't matter whether the variable is initialized or not. When this variable is declared, your compiler assigns a memory address to this variable occupying 8 bytes of memory space, just like the above. Even though there is no value associated with it, there is a memory address associated with it. Therefore, you can use the ampersand double val and assign that double val to this double pointer. And the assumption is that your double pointer is declared as double star, DOUBLEPTR. And you probably had it initialized as a null pointer. You can assign the address of double val to it. So this is one example illustrating the use of address of in the context of pointer. Let's show another example. Let's use the actual address to illustrate. This is the same example. Declaring a double variable with a value means that inside this memory address, the value is 0. Similarly, inside this memory address for double pointer, we have undefined value right here. However, as soon as we execute number 3, this is number 1, this is number 2. Number 3 tells us that double pointer now contains the memory address of double val. Therefore, the memory address of double val becomes the value of your double pointer. This illustrates the address of operator and how it is used in a real sense. Let's move on to talk about the other pointer operator, dereferencing. Let's take, for example, the same thing that we had here. We use this extras, which sits in front of the double pointer, to indirectly refer to the value that this double pointer points to. This operator is what we call dereferencing operator, and sometimes we call it indirection operator. This operator is really a complement of the ampersand address of operator. It is a unary operator that returns the value of the variable located at the address specified by its operand. Translation: this dereferencing operator is used to get the variable pointed to by a pointer. When you have a pointer, you need some way to access the memory that it points to. When it is put in front of a pointer, it gives the variable pointed to. This is an L value, so you can assign values to it or even initialize a reference from it. Let's look at this closely. Recall that in computer science, an L value refers to memory location, which identifies an object. In this case, double pointer is a L value. When you place this dereference operator in front of an L value, you get back the value that this pointer points to, which means this. So when you print out a star double pointer, you're getting 0, which is the value of your double val. Now, later on, if you change this double val to a value of 10.2 and invoke star double pointer to dereference it, your cout here is going to output 10.2. We must note that this dereferencing capability as applies to pointers is a very powerful concept, because this allows you not only fetch your pointer's value but the value of the object that this pointer points to. So no longer do you have to pass your entire object by value into a function. You can pass it by, for example, pointer, and by dereference that pointer later on, you get back the value of the object that you passed to that function. This slide illustrates the effect of what we just discussed. When you dereference a double pointer, you get back the value of the object that this pointer points to. So this object is double val with a value of 0. Let's look at some operator examples. The very first line shows an inline view of 4 variable declarations, x being an integer, y being an integer, and x pointers and y pointers being an integer pointer. The pointers are initialized to a value of no pointer, whereas the 2 integers are uninitialized. The next 2 lines initialize both x and y to a value of 10 and 20, respectively. And then we assign x pointer and y pointer to address of x and y, respectively. Note that because x and y have already been declared on the stack, we are able to fetch the memory address of x and y and store them in x pointers and y pointer. Both x and y pointers are also located on the stack. Now, let's apply indirection operator or the dereference operator on x and y and see what we have. The first x, when printed, it's going to give us 10. Y is going to be 20. When we dereference x pointer, which points to x, we're going to get back x's value, which is 10. When we dereference y pointer, which points to y, we are going to get back y's value, which is 20. Let's look at the next line. Y pointer equals x pointer. This is permissible because we know pointer is assignable. So y pointer now equals x pointer. Both are the same. Remember, when we dereference y pointer, this is the same as if we dereference x pointer, which we know the value of 10. What about this very last line? When we print out x pointer, we're getting the value that is stored inside the x pointer. And this value is a memory address of x. So it's going to be some sort of hexadecimal value, x times something, being the very first in print. Then we print out ampersand of x, which is also the memory address of x. Therefore, the last line of code gives us 2 memory addresses of the same side by side.